So let's try row reducing. This is an adjacency matrix. It's a 4 colorability matrix using the magic average. The magic average was, what did we decide that it was? So z equals tx minus plus 1 minus ty, where we're going to do this arithmetic mod 4, and we chose t to be 3, which, since it's relatively prime to 4, that means that the magic average is going to work the way that we want it to. And we got the equation z equals 3x plus minus 2y, which we rearranged into 0 equals 3x minus 2y minus z. And then we traded out negative 2 for positive 2, which we can do in z mod 4. And we traded negative 1 for positive 3, which we can do in z mod 4, and that's where this form came from. And by labeling each of the crossings in a diagram for the knot that we're working with, which was 6-1, 6-2, which one were we using? 6-2. 6-2. We ended up with this matrix. So let's try row reducing. Again, the valid question is, what's our ultimate goal in row reduction? And it is to get the entries underneath the diagonal all to be equal to 0. Once we've done that, we haven't gotten reduced row echelon form yet, but we've gotten it into a form where we can tell how many free variables there are, which is the thing we care most about in counting the number of 4 colorings in this example. So let's try and be systematic about this and go from the top left down to the bottom right. And the first entry that's suspect here is this 2. So if I want to get rid of this 2, then what I ought to do is either add something into this row to make that 2 into a 0, if I can. But I only have rows that have 3s at my disposal, right? So what I want to do is I want to add how much do I want to add to this in order to make it turn into 0? I need to add 2 to it. So I need to multiply this row that has 3s in it by something that's going to give me a 2 when I multiply. So 3 times blank is equal to 2. And we look in our diagram, 3 times 2 is equal to 2. So if I take twice this first row, for example, and add it to this row, or if I take twice the row below it and add it to that row, then that's going to do what I want it to do. In fact, I probably want to do the latter, because that will make sure that these entries both stay 0 also. So the operation I'll do is twice row 5 added into row 4. And row 4 gets replaced by that. Whoops. So if I do that, so after our first row operation, we've succeeded in clearing out one of the non-zero entries in the first column. Now the next thing is to try and clear out the next one, so that our first column has all zeros below the diagonal. So we'll put our target on that 3 right there. And for that, I think it's a little easier to see what we have to do, because the only way we can cancel out this 3 is by combining it with this 3 that's above it. And we can do that just by directly subtracting if we want to, right? So I can just take row 5 and subtract row 1 from it to eliminate that 3. So far, I'm not seeing a problem in actually carrying out the linear algebra that we need to do to row reduce this thing. So there's the result of clearing out that entry. Try and shrink this down a little bit. Then I would set my target on this last remaining 3. If something significant is going to happen here, we should see it happen pretty soon. And I think we'll see it happen at this step. So what I want is to clear out that orange 3, which I can do by, well, I can't add just this row to it, but I can, actually, maybe this is the problem now. Because how do I turn that 3 into a 0? Without undoing the progress that I've already done. Because I can't multiply this row, the second row, which would be the natural choice. I can't multiply it by anything that's going to, when added to this 3, give me a 1. All right? If I multiply it by nothing, I just try to add, make it into a 0. I can make it into a 1 easily by multiplying this row by 1 and adding it to this. 3 plus 2 is going to give me 1. But the difference between 3 and 0 is 1, and I can't get 1 by multiplying this row by anything. because 2 is not invertible. So at this point, we kind of hit a bump in the road. And it's not clear how to eliminate that 3. So this is probably why Sage wasn't up to the task of doing this. And it's also kind of provides an argument for why if we're trying to answer coloration questions one color at a time, one type of coloration at a time, these kinds of snags are likely to be common. Anytime that we have a composite number of colors in our crayon box, the possibility arises that the magic average is going to give us an equation which we can't row reduce adequately. And so, there may be matrices for which it's possible to row reduce them over Z mod 4, but this matrix is evidently not one. So at least we kind of let Sage off the hook a little bit. It's not Sage's problem that we couldn't row reduce this thing. So here was the matrix that, I'm going to comment this out for a second. Here was the matrix that you typed into Sage to try and discover whether Sage can row reduce it and give us the echelon form. But when you ask Sage to try it, it pops up with this error. And the content of this error is that no one has told Sage how to row reduce matrices over Z mod 4. And the good reason for that is that row reduction generally, successful row reduction, relies on our ability to divide by non-zero numbers. And because in Z mod 4, the number 2 cannot be divided by, we end up hitting this obstacle in our row reduction. It's going to prevent us from getting to even clearing out all the zeros underneath the diagonal. So this particular matrix is going to be a no-go. Even if we try some other commands, for example, I could ask it to try and find the kernel of this matrix, but it's going to give me the same error, which is really an error about the arithmetic field over which we're asking it to do these computations. So again, I'm going to treat this as a teachable moment, spin this as the observation that when we just do one type of colorability at a time, the individual vagaries of the modular rings of integers can interfere with our ability to determine colorability. And it may also be an argument for why, if you're going to study colorability as a knot theorist, you should try and study P colorability, where P is a prime. So 3 colorability is great. It's the easiest one to study. It's the smallest that's non-trivial. But 5 and 7 and 11 and 13 colorability, depending on how complicated your knot diagrams are, all of those we're guaranteed to be able to do with the linear algebra that's necessary to count the number of valid colorations. But if the number of colors in our crayon box is composite, then chances are pretty good that we're going to run into one of these obstacles and not actually be able to determine. So when it comes to 4 colorability, here's an option. If I want to know whether or not my knot is 4 colorable, why don't I put an extra crayon into my box? So I have 5 crayons in my box, let's say, and then do the arithmetic over Z mod 5 and find out, how many solutions there are for 5 colorability, and then check to see if any of those solutions actually don't use all 5 crayons, but only use 4. So that might be how we resolve this question, right? If I can't ask about 4 colorability because we can't do the linear algebra, let's instead ask about 5 colorability and then check my solutions to see if there are any 5 colorations that only use 4 of the colors. Because linear algebra by itself doesn't distinguish for us in between, say, trivial colorations that only use 1 crayon or colorations that use all of our crayons. The linear algebra by itself doesn't distinguish between those scenarios. So we have to do that ourselves in a post hoc way. Right? After we get the solution out of that system, we can go back to the well and ask, does my solution use all of the colors? So let's make that modification. We'll just do it right here inside of Sage. I'm going to add a color into my crayon box so that we're going to do our arithmetic over Z mod 5 instead. The other thing we need to do is modify the magic average. So it's going to change the coefficients in my matrix, although all of the non-zero coefficients should still at least be in the same locations as one another, right? The overstrands are still what they were before. The understrands are still what they were before. All we have to do is figure out how the magic average changes when we're in Z mod 5. The t that we choose for our magic average just needs to be invertible mod 5. So what are our options? What are the invertible elements of Z mod 5? 1 through 4. Every non-zero element, Z mod 5 is a field. So just for the sake of choosing something, I'll choose 4 as my invertible element. And then my magic average equation becomes z equals tx plus 1 minus ty. And if t is 4, 1 minus 4 is negative 3. Let me move my z to the other side, as we did before. And then just for readability, let's turn all of our coefficients positive. Negative 1 on the z is the same thing as positive 4. By the way, the x and z coefficients in this magic average always end up the same. What's a good reason for that? Which of the strands are x and z in a crossing? They're the unders. And what's important about that? Yeah, the magic average cannot care which understrand is which. There's a symmetry at every crossing. And so the two understrands will always be, this equation will always be symmetric with respect to an interchange of which two understrands we're looking at, right? So x and z will always have the same coefficient. If I make the negative 3 coefficient on the y positive, what does it turn into? Mod 5 plus 2. So the only thing we have to change to turn this matrix into our 5 colorability matrix is we'll just change all the 3s to 4s. And then do the arithmetic over Z mod 5. So there is our new matrix, 4, 4, 0, 0, 2, 0, and so forth. And then let's go ahead and ask Sage for the resolution to this. There we go. Oh, look at that. So I actually had asked Sage for a slightly different command. Instead of asking it to row reduce, I asked it what was the kernel of this matrix. Let me back up a step and ask it to do the row reduction because we're familiar with that output. But then we'll also talk about the kernel in a second. So there's the echelon form of this matrix. And what's the most important feature that we care about? Yeah, there's a single free variable. So what does that tell me about the 5 colorability of this knot? Right. The fact there's only one free variable means that we only get to choose the color of one of the 6 arcs on our own, and that one choice is going to determine the colors of all the other arcs in the same diagram. And so, similar to what we were looking at, the example we looked at last time, if we rearrange the equations that are left, each equation that's left has a 1 and a 4, and 4 is the same as negative 1 in Z mod 5. And so what the remaining equations are really telling us is x1 minus x6 is equal to 0, mod 5, or, to put a finer point on it, x1 equals x6, x2 equals x6, x3 equals x6, x4 equals x6, x5 equals x6. But x6 itself is free. So we get to choose whatever value for x6 that we want to choose. But as soon as we choose that value, all the other 5 arcs have to be colored the same color. So the only 5 coloration of this knot is a trivial 5 coloration. That means then also that the only 4 coloration of this knot will be trivial. Because again, the linear algebra doesn't tell us by default whether or not we're using all 5 colors in a 5 coloration that it discovers for us. And so if a 4 coloration exists, it will have to show up as one of these 5 colorations. Just happen to be one that doesn't use all 5. So for the knot 6-2, colored with the 5 coloration where we've chosen t equals 4 as our invertible element, here the system shows us that there is no 5 coloration. So the lesson here is that if your 5 coloration, if your search for a 5 coloration turns up a non-trivial solution, so here actually is a non-trivial 5 coloration for the knot 6-2, then your job is going to be to check that 5 coloration to make sure that all 5 colors are in fact being used. So in this situation, what would happen in your row reduction is that you would get more than one free variable. I think you just get 2 free variables in this example. And then by choosing a non-trivial, by choosing unequal colors for your 2 free variables that you now can choose, right? If you make one of them 0 and the other one 1, for example, then chase out those consequences for the rest of the knot and see how many of your colors actually get used. And in this case, for this coloration, you find out that all 5 get used. But you can imagine a scenario in which that doesn't necessarily happen, and that maybe there exists a solution that only uses 4 out of the 5. But really, that's something that you need to check, because linear algebra is not going to do that for you.